z equals what, x squared minus y squared? Like that? What happens if instead you did y squared minus x squared? What's the only thing that changes? The whole thing what? Rotates 90 degrees. That's it. The whole thing just rotates 90 degrees around the z-axis. That's it. But this right here, you pick a z-value, you make the graph. You pick a z-value, you make the graph. Each one of these, though, so when you graph, for example, when you plug z equals 1, you're going to get this and this. What's that called? Hyperbole? Yeah. Yep, correct. So you ask the question, what happens if you don't actually get the equation? What you're going to need to do is visually do it in your head or know an approximate equation for it. Like you should be able to look at that and go, that is a hyperbolic paraboloid. Like you don't know about the exact steepness, so you don't know if there's like a multiplier in front of x or y. Assume it's the basic one, and then you could run it. Yeah. So did you pick z values? Is that how you did your contour diagram?
Oh, I did.
Oh yeah, so you asked about 6. So you literally, your contour diagram exists on an xy plane. Now the thing is, what's interesting about the perspective here, look up here, what do you see about this? You do see that x goes to the right and y goes up, correct? It's an interesting, we reorient to that because that's how we look at two-dimensional graphs, correct? The thing is, if you start with 3 dimensions, right? If you started with this and z, you have y and you have x, if you looked down, if you're looking down on this, if you look straight down, depending on which way is up for you when you look down, it changes which way is, like, if is x up or is x. The reason they go with the original orientation is because what are you most familiar with in terms of a two-dimensional graph? What goes up and down? Y. And what goes side to side?
X.
Theoretically, could you reorient and go x up and y to? Yes. Why don't we do that?
Complicated.
It just gets it more complicated. Pick a standard and stick with it. Okay. So when you do this, you pick a value for z. So what value of z do you want to do first? What z value do you want?
0.
How about 0? So if z is 0, what's the equation? 3y equals 0. So x plus y is equal to? So y is equal to?
Negative x.
So y is equal to negative x. What does that look like? A terrible line, but there it is. And that's a terrible line. Sorry. And there's a line draw tool that I should use, but I'm not going to. So what do you have to do with this one? You have to label it what?
0.
So this is 0. So then what do? You pick another z value. What z value do you want to pick? How about 3? So how about you have 3x plus 3y is equal to 3. So x plus y is equal to 1. So y is equal to negative x plus 1. So where's that going to be? Oh, it hits here. This is a 3, right?
So all of these are parallel.
Correct. They're all parallel.
And I kind of made
Correct.
a generalization.
Yes.
Well, it's a plane. Like when,
it's a plane, so they better be parallel. Yes. Yeah.
Well,
yeah.
But there is, this, linear term.
Yeah.
That makes a ladder. So
yes, exactly. A ladder in a certain direction. Yeah, exactly. So then this line right here, if I just draw that one in, which one's that going to be? 6, assuming that this is 1 and this is 2 right there. Yeah. So can you keep on drawing them? Yeah, absolutely. I hope so.
Continuous parallel.
11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. So there's a pattern. Nice. Okay, we're excited. Saying here, look what it says. This means if x is decreased by 1 and y is increased by 1, so then what did they plug that into? What did they plug it into?
F.
They just plugged it into the original, right? They plugged it into the original equation, so you have your x minus 1, you have your x minus 1. So wherever there was x, what did they plug in? X minus 1. So then wherever there was y, what did they plug in? Y plus 1. So they have y plus 1, y plus 1, y plus 1. So what did they do after they did that? They cleaned it up. And they did some creative manipulation. And what did they end up with? You see this right here? What is this right here? This is what? That is z. That is the original, right? That is f of xy. So what's the only thing that got added in? That plus 1. So that's how you prove it. This is challenging. This is absolutely challenging. I think also it's not trivial. Well, actually, it cleans up pretty well. The algebra is annoying, right? Because you end up having to factor a little bit. It's annoying.
I think it's a little bit.
Yeah. The other thing that's hard when you look at answer keys like this is it gives you 3 clean lines, and you're like, okay, I understand what they're doing, but they leave out the fact that going from here to here is not trivial. By writing it down, it's like, oh, it's really clean. Of course it multiplies that, but then you realize, nah, maybe not. Okay, I mean, here's the challenge. Let's just take a look at this for a second. If you look inside here, what do you have here? You have the x right there. You have minus 1 and plus 1, so that cancels, right? So that's where this comes from, right? Then you have x, minus 1, y, and then plus 1. and then you have minus 1, and that's where this comes from, correct? Oh, look, it actually isn't that bad. And then you have y plus 1, which is right there. Oh, it's actually not too bad. Oh, I'm sorry. It was not that bad. The book frequently will, though, do some unbelievable factoring, and you're like, I just don't see it. It's right there in front of me. And then you drill down into it, and you realize it is impossibly hard. Like, it's really hard. Like, the book is nasty. Answer keys are generally really nasty about, like, simplifying logarithms. So, like, clearly this thing equals 7. And you're like, no. Do you know what the worst word is in all of math?
Clarity.
Clearly. I told you this already, right?
Yeah.
Clearly or obviously. It's never a word you ever want to use or ever see written in a math book, because either you understand it, you're okay, or the book is insulting you. Like, no, it's not clear. No, it's worse, and I hate you now.
My favorite word.
So the question is, if I said you have a plane, it hits the z-axis at z equals 5, and it has a slope in the x direction of -1, and it has a slope in the y direction of, let's say, a slope in the x, 2 in the x direction, and a slope in the y direction of 1. So here's the thing. If you're on a line in 2 dimensions, you can either go left or right, right? Usually you go to the right. It's dy dx going to the right as x increases. The challenge now is that if you're on a plane, if you're on a surface, you can go in many different directions, right? You could walk parallel to the y-axis. You could walk parallel to the x-axis. Does everybody see what I'm trying to say here?
Yeah.
So if you're standing on a surface, you could either walk north or you could walk east. For example, you could walk south or you could walk west. The idea is that positive x direction is one rate of change. Positive y direction is another rate of change. So the question is, how would you write a plane that has these properties? How would you write a plane that has these properties? Yeah.
I'd have to do partial.
Yeah, you can think of it in terms of partial derivatives, but since we haven't done them, how would we piece this together? So when it crosses the z-axis, what is the x-coordinate when you cross the z-axis?
So 0 is...
0, just say 0, okay. What's the y-coordinate when you cross the z-axis? When you're on the z-axis, what's the y-coordinate? Y and x are both what?
0.
Yeah, so if I have the point 0, 0, z, what axis am I on? The z-axis. If x and y are both 0, you are guaranteed to be on the z-axis. So if x and y are both 0, what's the only thing that's left in this equation? So you have something x plus something y, but what do you have to put? What do you have to add to this thing? If x and y, a constant, and we know that constant has to be what? 5. So we've built this so far. We have some plane where z equals 5 plus some coefficient x plus some coefficient times y. Do we actually know what that coefficient is for x? Ah, we do. What is it?
2 and 1.
Yeah, we actually know. I already told you them. Look, the x direction change is what? 2. So it's going to be 2x. And what about the change in the y direction? 1. If you just change x, what's the rate of change? Sorry, if y is changing, what's the rate of change of y? 1. What's the rate of change of x? 2. Does that match this sentence?
Yes.
Yes, it matches this sentence. Excellent, excellent, excellent. The idea here is that we now have z with respect to x and the rate of change of z with respect to y. Yes, Jesse? So yeah, it's a plane, but what can you specifically decode what each of those values are? For example, what is x naught, y naught, and z naught?
Or initial.
Any point, right? Any point. Any point, because this is a plane, it doesn't matter what point you set. Right? Remember when we did lines in parametric land? Did it matter what point you started at? No, because if you start here and go back and forth, it's the same thing as starting here and going back and forth on the same direction. Okay, what about m and n?
Slope.
Yeah, so this is the slope in the what direction?
X direction.
Slope in x direction. So what's another way to say the slope? That is dz dx. And then what's n going to be?
dz dy.
Slope in the y direction, so it's going to be dz dy. Exactly. Nice. So if you find those things, you can construct anything you want with as long as all three of them are on the same line. So that right there, if I ask you, those are the 3 points. We can label them A, B, and C. If I wanted to come up with the equation for the plane that goes through those 3 points, well, let's try building it. What are the main things we need to know? Well, do we have a point? Well, in fact, how many do we have?
3.
3 of them. So we already have more information than we need with regard to an initial point. But we need dx, dz, dx, and dz, dy. How do you figure that out?
Find a difference.
Find a difference where, though?
Z. Where
Between, yeah, you have to find specific to which 2 points, though. There are specific ones that work in specific cases here.
The difference is not zero.
Well, hold on a sec. So you want to find, this is dz, dx.
A or C or
Okay, so what about A? What do you notice about A and B? What's something you notice about A and B?
it's the same as
The x stays the same. The x stays the same, right? So the x coordinate stays the same. So what can you then find if so between these two, you know that the x coordinate x stays at 1, right? So which one can you find here?
dy dz.
So you can find dy, it's not dy, yeah, dz dy, right? Because now height is z, so dz dy, what's that going to be?
Yeah,
3 minus 1 over negative 1 minus 0. Does that work?
negative 2.
3 minus 1, negative 1 minus 0. Does that work? So what do we think? It's 2 over, which is going to be what? Negative 2. Okay, so we chose those because x stayed the same. But now what else do we have? A and C. When you do A and C, what stays the same? Y is stable at what? Y is stable at 0, right? So which one can we find now? dz dx. So what's that going to be? dz is going to be negative 1 minus 1 over 3 minus what?
1.
1. So you end up with what?
Negative 2 over 2 is a negative.
Negative 2 over 2. So what is it?
Negative 1.
So we just found, in terms of this formula, this is the x one. So that's m, and this one is n. And again, I don't know why they use m and n all the time. They sound and look the same. Great, right? Then which point do you want to use? We have to pick a point, right? What point do you want to use? Let's use b. I don't like the zeros in there. Zeros kind of just make things a little too reductive for me. So if we use b, what do we think this is going to be? Z is equal to what? What's z naught? If this is the point we're using. 3 plus, what was m? So not plus, it's going to be minus what? Minus 2 times x minus, what's x naught? 1. And then was it minus 1? So minus y minus what? Plus 1. There it is, right there. You just figured it out. You just figured it out.
That's the equation of
That's one equation for the plane. Are there other ways to write it? Yeah. Sure. You could use different initial points. Exactly. And theoretically, should it reduce to the same exact plane? Yes, it should be the same. Does it go through those 3 points? Let's test 1, 0, 1. When x is 1, so let's test a point. So we think this works, but it should also go through the point 1, 0, 1, right? Maybe we got it wrong. Let's try it. If we plug in 1, 0, 1, we know that 1 is supposed to be equal to 3 minus 2 times, what's x in this one? 1 minus 1. No, x is 1. Minus 0 plus 1, right? So what do you get? 1 equals 3 minus 2 times 0. Minus 1. Does it work? So did we make a mistake somewhere? It doesn't seem to go through that point, does it? So what's our mistake? Let's find it. Kids, we figured out, what is this? dz dy, right? And this is dz dx. That's not m and that's not n. What did we do? This is just what? This is just n and this is m, right? Yeah, okay, hold on. So theoretically, that should clean it up. I was like, I thought we did that really well. You guys handled that very nicely. So theoretically, let's clean this up here. It should be what? It's just that, and then what's this should be? Minus what? Minus 2. Now, does that work? Yeah, if you plug in 1, 0, 1, you get 1 equals 3 minus 0 minus what? Does 1 equal 1? Yay, it works. Okay, great. We just labeled it improperly. Yeah. So if you find the rate of change of y, make sure it goes in front of the y's. Exactly. Nice. Okay. 9 points. These are the actual points right here. Those are the actual points right there inside the box, which I'm doing a very poor job of highlighting properly. So if there are 9 points, what is one of them? For example, what does this point mean? The x-coordinate is 1, the y-coordinate is 2, and the z-coordinate is 1. So given those 9 points, can you tell me if those 9 points are on a plane or not? How can you tell me that, Jesse? How could you tell me if these 9 points are on a plane? What would you have to check? You could. You could pick 3 of them, build an equation, and then plug it. There's a quicker way, though. What do we know? The rate of, so, James?
You could set, make it a contour diagram, so when the z's are the same,
Okay. We don't set the z's the same. When we found these slopes, right? When we did these subtractions, we were looking for when x's were the same or when y's were the same, right?
So they have the same dx, dy.
Oh, what can't change?
The slope.
The slope in each direction. So you said it, James, and you said it, Matt. dz, dx has and
dz, dy.
dz, dy have to be. They have to be constant, right?
They have to be in linear relationship.
Correct. So let's take a look at this. Let's look at this line right here when x stays at 0, right? Let's say x stays the same. You go up 1 with y, what happens to z? Z goes up 1, right? You go up 1 again, what does it go up?
4.
It doesn't go up 4, it goes up how much?
3.
3. Can this be a plane?
No.
No, it can't be a plane. It can't be a plane. If you see why? Because look, y went up by 1, and what happened to the z value? It went up by 1, right? But then you go up 1 again, and what happened to the z value? It went up by how much? 3.
So you go like
Exactly.
this.
So if you So not only, kids, not only do you have to check these, but what else do you have to check? You also have to check down as well, right? And what do you notice?
They're all the same.
It's all the same gap. So is that a plane? Do you have any idea what the equation is right now?
No idea.
Could you if you wanted to?
Yes.
Absolutely. You can also tell really quickly what is, if you hold x constant, what is dz dy?
Oh.
Every time y goes over 1, what happens to z? Goes up 3, right? But what about dz dx?
2.
It goes, every time x goes up by 1, z goes down by 4. So then you just pick one point, and it's just like parametric, you pick an anchor point, and you go with it. Yes, last question.
So out of those 3 sets, if one says the